right? So we want to compute the integral of an equivariantly closed form on the manifold M. And what we showed in the last hour is that we can do the integral upstairs on the blow up. And in a minute, you'll see that there's a big advantage to doing it on the blow up. So let's see. Let's continue. So we have now, since this sigma star phi is equivariantly closed, you can write it as bxk sigma star phi. Okay. Upstairs. Okay. And then now you can apply Stokes' theorem. So when you apply Stokes' theorem, you get k sigma star phi, which you integrate on the boundary of the blow up. Okay. Now the boundary of the blow up, I have erased it, but the boundary of the blow up are these spheres. Okay, one for each fixed point. So it's the integral over the union of the spheres, where P is the fixed point. Okay, and the sphere. A sphere has an orientation like this, which is opposite the orientation of the boundary. So you need to put a minus sign here. Okay? And so well, these spheres are disjoint. So what you get is minus the sum over the integral of the integral over each sphere, okay, of k sigma star phi. Okay. Now k is this. There's a minus sign, so that minus sign is going to cancel out this minus sign. You get theta over u. 1 plus d theta over u. Okay, so that's k. Okay. And then sigma star of phi. Yeah, let's leave it as sigma star of phi. Okay. Okay, now phi, well, phi, we should assume that phi has a degree. Okay. Let's say phi. Let me see. Phi has degree. Phi has degree 2n. Okay, that's part of the hypothesis. Yeah. So assume. Yeah, because we want to calculate the integral of phi over n. So phi should have degree 2n, the dimension of the manifold. Then phi is, yeah.
Map K is made the localization of Cardan form to localization of Cardan form. So why is the integral of
Oh. Oh, right. There's a u there. Yeah. Basically, when you integrate, you don't do anything to the u. Okay. So, yeah. So, I mean, whenever you have a map on an algebra, there's an induced map on the localization, right? And so the way, if f, if you define f on any R of U algebra, then there is an induced map, and the induced map is defined this way, right? So you basically leave the u alone. Yeah. So we have an integral. So basically, what I'm saying is that the integral of a localized form is just the integral of the form over u, over the power of u. Okay, so yeah, good. Yeah. So this k, it was defined on the k is actually defined on the localized Cartan model, and when you integrate, you don't do anything to the u. It just comes out, whether it's upstairs or downstairs. Okay? Now, if phi has degree 2n, then it will be of this form, right? It's a form of degree 2n plus a form of degree 2n minus 2 times u plus, and so on. And then the last term will be some function times u to the n. Okay? Yeah. So phi is in the Cartan model. Okay? If it has degree 2n, it has to look like this. No, we don't consider phi with higher degree, because basically what we want to integrate is this, an ordinary form of degree 2n, right? So you see, then the integral of phi, well, when you integrate, you just integrate the form, but all the other terms will give you 0, because all the other terms have a form that has degree less than the dimension of the manifold. And so you see, so the integral of the equivariant form is the same as the integral of this ordinary form. Mm-hmm.
Phi, if it is of higher degree, then still, after you integrate, there will be still some part which is non-zero.
Right. Yeah. I'm only stating the theorem for a form of the same degree as the manifold. There is a statement for an arbitrary degree, okay? But for application, this is what you want. So we'll just do this case. Yeah. Okay. So you have this. And so we need to pull it back, pull it upstairs. We need to pull it upstairs and then restrict it to the sphere. the integral so sigma star phi is restricted to the sphere. You pull it back to the blow up, and then you restrict it to the sphere. Okay? So, in other words, restriction is the map induced by inclusion. So you have the sphere that's included in M tilde, and then you have the blow-up map, sigma, okay? And the sphere maps to the single point P. So you have this commutative diagram. So from the commutative diagram, you see that if you take phi, you pull it up, and then you restrict to the sphere, it is the same as first you restrict to the point, and then you pull it up. Okay? But what is I star of phi? What happens to phi when you restrict it to a point? This is phi. What happens if you restrict this to a point? Yeah, all the terms will be zero because this is a 2 form, this is a 2n minus 2 form. So restricted to a point, they all become zero. You are left with only this term. Okay? So this is sigma star of f of p. You evaluate f at p, and then you still have your u of n. Okay? And this is f of p, u of n, because when you pull back, u doesn't do anything. And the constant pulls back to a constant. Okay? And so, so the integral becomes easier. Now, so let's go to this board. Yeah. So we started with, I think I have erased it. This was the integral of phi over n. Okay. It's equal to the sum over the fixed points of the integral of this times this restricted to the sphere is just f of p u to the n. And then, now, when you integrate, right, you leave that u alone, so you're only integrating the form. So actually, there's only one term that you are integrating, right? Because everything else will be zero for degree reasons. What is only the single term that you are integrating? Yeah. Yeah, it's just theta, d theta to the n minus 1. That has degree 2n minus 1. Okay. And then this is divided by u to the n, and then you have f of p u to the n. So the u to the n will cancel. And f of p is a constant, so it comes out Yeah, so we need to calculate that integral over the sphere. Now, we have an explicit formula for theta. Okay. That sphere is the unit sphere in the tangent space at P. And then we have this formula. We call that theta was equal to 1 over 2 pi. The sum, as j goes from 1 to n, of 1 over mj times minus vj duj plus uj dvj. Okay? That's the theta on the sphere. Okay? It's a one form on the sphere. And so d theta is 1 over 2 pi, the sum of 1 over mj, okay, minus dvj wedge duj. I can switch the two. It becomes duj dvj, and this also gives me duj dvj. So I get 2 duj wedge dvj. Okay, and so the two cancels. Okay, so that's d theta. And now I have to take d theta to the n minus 1. Okay, okay, so pi is raised to the n minus first power. And then I multiply n minus 1 of these together. Yeah. Now, if the j's are the same, then you'll get 0 because you'll get a repeated duj. So they have to be all different. Okay, but you have n minus 1 of them. Okay? So you are going to get du1. I'm going to omit the wedge sign. du1, dv1. You just miss one of them, right? You have n minus 1. N minus 1 terms. So there'll be one that's missing. There's one j that's missing. Right? When you multiply them, n minus 1 of these together, you'll get this. Okay? One of them will be missing. Now, for a fixed j, how many of these will you get? See, when you multiply them out, you will get these guys in any order. Right? Every order will occur once. And you rearrange them into this increasing order. You could do that because these are two forms, so there's no sign. So you have all possible orders. So you actually will get n minus 1 factorial terms like that. Okay? And then you omit one j at a time, right? So that's what you get. And, oh yeah, and then there's, and then it has to be divided by the product of these m's, but missing one of them. Okay, you get that. Okay. Okay, and now I have to multiply this by theta. So theta d theta n minus 1 is equal to, okay? Now, just a minute, where was the form? Oh, yeah, so here's the formula, and I multiply this by theta. So I'm going to get 1 over 2 times pi to the n. Okay? Okay, and then you see, now this multiplied by this usually will give you 0 because there's a repetition. So the only time it's not 0 is when you have a duj and you don't have a duj. Okay, so and in that case, this mj is going to fill that in. So you are going to get the sum of 1 over m1 to mn, all of them, and then minus vj, duj multiplied by this. duj goes there, and so dvj is missing. So you have minus vj du1 dv1 dvj is missing, and then dun dvn. That comes from this times this, and then this times this will give me plus uj du1 dv1 duj missing, dvj, dun, dvn. Okay? Now, and then I still have this m minus 1 factorial. Right? Yeah, okay. So do you agree that I get that? Now, what is this? Well, I can take out the m1 to mn, okay? And these are the exponents evaluated at p. Yeah, this is on the sphere SP 2m minus 1. And then what is this? The sum of all these 2m minus 1 forms. Yeah, it's precisely the volume form of the sphere, right? The volume form of the sphere, you know, you have that variable, and then you have the dxi missing, and that's precisely this. So it's this is precisely the volume form of S2m minus 1. And that is a sphere about the point P, okay? And yeah, so the integral of theta d theta to the m minus 1 over the unit sphere about P is going to be n minus 1 factorial over 2 to the pi to the n, and then 1 over m1 to mn at p, okay, times the surface area of the sphere. Okay. The surface area of the sphere is given by this formula. The sphere of dimension 2n minus 1. So it's 2 pi to the n over n minus 1 factorial. And yeah, so actually you get a lot of cancellation. You just get 1 over the product of the exponents at p. Okay. And now you go back here, you put it into this formula, so you get fp over the product of the exponents. So finally, this is equal to the sum over the fixed points f of p over the product of the exponents of p. Okay. And that is the localization formula. Okay, so which is and this is equal to the integral of the top form in phi. That's an ordinary form. Okay. So this gives you a way to calculate the integral of an ordinary form. You first have to find an equivariantly closed extension, and that will give you the f. And then you can use this formula to convert an integral to a sum. Okay? Yeah. Now, this is for a circle action. Okay. We now want to generalize everything to other groups. Okay. So our group will be a Lie group. But we will assume that the Lie group is connected, because for a connected group, you see, there's a condition for invariance in terms of the Lie derivative. You know, if the group is not connected, then you don't have that invariance condition. Okay? Yeah.
In the derivation here, I still have a little bit of an easy feeling, since you have to do restriction, you take a pullback by I,
Yeah.
inclusion, and there was the homotopy map there, the K, which is of degree -1. So do we need more justification for that statement on the first line there, or that is trivial?
You see, the thing is that restriction is a ring homomorphism. Okay. So yeah. So we had K sigma star phi, right? That was the thing that we were integrating on the sphere. Now, what this means, I mean, this K, this is actually defined on the blow up, on the entire manifold. So when you say I integrate this thing to a submanifold, what I mean is that I restrict, and then I integrate, right? When I restrict, then it becomes a form here, okay? Now, but I star,
I star K and also sigma star.
that's right, yeah. So this is I star K, I star sigma star phi, because I star is a ring homomorphism.
But it's better to write I star alpha K.
Oh, K is, yeah, K is multiplication by alpha, right, yeah. And then, so this part here gives me Fp u to the n. And this part, it just says, yeah, so I restrict these thetas to the sphere. Right? And the formula that I wrote down for theta was when I restricted theta to the sphere, right? Yeah. Right. Yeah. So I star of theta, normally theta has 1 over sum of uj square vj square. But when you restrict to the sphere, that becomes 1. So that disappears, which is that formula that we wrote down. Okay, yeah. Okay, so I'm going to start, a new lecture. Yeah, so this lecture 33 has the continuation of the proof, and then we want to look at the Cartan model in general. For a connected Lie group, not just a circle. Okay. So let G be a connected Lie group acting on a manifold. M, say on the left. Okay. So I want to review a little bit the Weil algebra and the Weil model and the Cartan model. Okay. So we choose a basis x1 to xn for G, which is the Lie algebra of G. And then we have a dual basis, theta 1 to theta n. For G dual in the exterior algebra of G dual. And then we have U1 to UN. It's the same dual basis for G dual, but in the symmetric algebra. Okay. So the Weil algebra is WG. It's the exterior algebra of G dual tensor with the symmetric algebra of G dual. And in terms of a basis, then it's the free exterior algebra generated by the thetas. And the symmetric algebra is the polynomial algebra generated by the U's. Now, on the Weil algebra, I have three operations. I have the contraction, the exterior derivative, and then the Lie derivative. Okay? So, for x in the Lie algebra, what is the contraction of Ix with theta I? Theta I is in G dual, x is in G, so it's just theta I applied to x. You get a number, okay? And what is Ix of Ui? How did we define Ix of Ui? It was 0, because Ui, there's a map, the Weil map, that sends Ui to the curvature form. And the curvature form is horizontal. So Ix of the curvature is 0. And you want that Weil map to preserve these Ix. So you have to define it this way. Okay? And then what's D of theta I? Remember that? D of theta I. See, the theta I was supposed to map into the connection form, omega I. And so D of theta I, it should be the thing that goes into D of a connection. And D of a connection is, it's minus 1/2 the sum of, let's use K here, and then Cijk theta I which theta j plus uk. Okay? Because that's a formula for D of a connection form. And then duk is equal to, so you need a formula for D of a curvature form, which is given by the Bianchi identity. And the Bianchi identity says that this is Cijk uk theta j. Okay? Ui theta j. Okay, so that's how we define D. And then you extend D to a derivation on the Weil algebra. Okay? And to an anti-derivation. And then, how did we define Lx, the Lie derivative? Yeah, it's just Dix plus Ixd. Okay? Yeah. And so, now that's on the Weil algebra, and then an algebraic model. Okay, we want to have an algebraic model for the homophobic quotient. So you first have an algebraic model for EG cross M. Okay. Now the Weil algebra, it's an algebraic model for EG. So then algebraic model for EG cross M is the Lie algebra tensor with the differential forms on M. Okay? And IX and D extend to this tensor product as antiderivations. And LX extend as a derivation. Okay? And then an element in the tensor product, so an element A in the tensor product is horizontal if, okay, what's a condition for an element to be horizontal? Yeah, IXA is 0 for all x in the Lie algebra. Okay? So horizontal means that if you apply to a vertical vector, you get 0. And it's invariant. Okay, invariant means that it under under multiplication, under the pullback by multiplication, it stays the same, but then we show that for a connected group, it's the same as saying that the Lie derivative is 0. Okay? And it's all basic if it's horizontal and invariant. Now, instead of checking it on all elements of the Lie algebra, you can also just check it on a basis. Okay, so because IX and LX are linear in X. So horizontal can also just, you can just check it IX on a basis. Okay, and then invariant can also be just checked on a basis. Okay, and I'm going to introduce a shorthand. So I sub I is IXI, L sub I is LXI, and then AI is AI1 IM, theta I is theta I1 wedge theta IM, and that I will also just omit the wedge sign, okay? So I introduce these shorthand. Okay. Now the first theorem is that the horizontal elements in this tensor product is precisely just the symmetric algebra tensor with omega n. Okay? So the theorem is that there is an algebra homomorphism. Algebra isomorphism. Okay? So this identifies the horizontal elements. Okay, I'm going to stop here, and then, next time we will prove this theorem. We'll continue with this. So we will identify the basic elements in this tensor product, and that will be the algebraic model for the homotopy quotient. Right? Because the homotopy quotient is a base of a bundle whose total space is the Cartesian product. So next time we'll work out the Weil model and then the Cartan model for a general connected Lie group. Okay? And then we can generalize what we have done. Okay? But the localization formula is true only for a torus action. So we'll generalize the Cartan model to a connected Lie group, and then we specialize to a torus. Okay? Okay, So I will see you on Friday. Now on Friday, you have a problem.